everyone. So today is the last day of the summer school. So our first speaker is Dr. Neeldhara Misra. You're all familiar with her because she's already given a talk. In any case, let me give an introduction. So Dr. Neeldhara Misra is an inspired faculty fellow in our department. She did her PhD in IISc Chennai. Her areas of interest include design and analysis of efficient algorithms for hard problems. In particular, she's interested in parameterized algorithms. So today she'll be talking about cheat codes for hard problems. We're looking forward to your talk, Neeldhara. Thank
you. Okay, everyone hear me? Yay, okay. So good morning and thank you for coming. If I were you, I would be sound asleep by now. So, so I'm really glad you're here. Anyone recognize this comic? Anyone follow XKCD? Okay, great. Okay, so this comic is really just showing a poor traveling salesman trying to figure out his route, okay, and his friend working around the problem by selling off eBay so that he doesn't have to travel at all. Yeah, so that's certainly a perfectly legitimate way to solve hard problems by avoiding them completely so that you don't have to solve them. But we'll see a couple of other methods as well during the course of this talk. Okay. So given that a lot of people have introduced things like graphs and problems associated with graphs from the ground up, I'll assume some terminology, but if there's anything you're uncomfortable with, just stop me right there, yeah? And feel free to interrupt me in general. So our starting point is going to be this idea that some problems are tougher than other problems. We'll not try to justify this belief right away, rather we'll just go with it, and hopefully you'll be convinced about why people feel that there is sort of a disparity in the difficulty or apparent difficulty of solving problems as we make progress in the talk. So our starting point is this class of problems that we call NP. You saw this in the PNP talk. So anyone remember what NP was? Precisely. Okay, that's excellent. So, so NP is sort of this large collection of problems which have the property that if somebody gives you a solution to the problem, then you can easily go and check that the solution is indeed a solution. One example would be traveling salesman. Okay, that's a bit icky. The traveling salesman problem asks for the root of the shortest, the smallest cost, let's say, right? So suppose I come to you with a route and I claim that this is the route with the smallest cost. How will you verify it easily? It's not completely obvious. How will you verify it easily? Mathematically. Can you elaborate a little bit? Yeah, mathematically, sure. Intuitively, it seems that if you have to actually confirm that the route that I've given you is actually the cheapest, you'll have to compare it against all other possibilities, right? And it's not clear that that's easy to do, okay? I mean, you can certainly do it, like we were talking about finding monochromatic triangles and cliques yesterday. Yeah, if somebody has to claim that here is a configuration which doesn't have a monochromatic triangle, okay, it's harder for me to convince you that there is no monochromatic triangle compared to convincing you that there is one. If there is one, I just point to it and you say, okay, 1, 2, 3, that's just 3 steps. Yeah, if I have to convince you that there's no monochromatic triangle, you have to actually verify every combination of 3 vertices and confirm that there is no monochromatic triangle. That's a much longer procedure. In the case of verifying that the tour that you have, or the one that I've given you, is the cheapest, you have to compare against all other possible tours. How many? How many? 2 power n. Okay, what's a tour? It's a sequence of cities, right? How many sequences of cities? N factorial, yeah? N factorial, and N factorial is certainly not going to be quick. Okay, so that's why usually problems in NP are phrased as decision problems, meaning that you give me a yes/no question. Don't give me an optimization question. Okay, is there a tour that's going to cost me 15,000 bucks in air tickets or train tickets? That's all that I want to know. I don't care about opt. Yeah, I have 15,000 rupees to spend. Okay, on my tour. Can you give me one that costs this much or less? Less is fine. Now if I give you a tour, can you verify it easily? Just add up the costs. Check if it's less or equal to 15,000. That's simple. Yeah? So that's kind of the motivation for phrasing questions as decision questions rather than optimization questions. Think about most problems that you find interesting. They're going to fall in this category. You saw max cut yesterday. Is there a split of the graph so that at least k edges cross the cut? I give you a split, you count the edges, easy. Okay? Is every problem in NP? Sounds easy. How many yes? Oh, okay. What if you have to convince me that there is no cut of size k? What if the question is, does the graph not have a cut of size k? Can you give me a solution that I can verify easily? Yeah. Yeah. So remember that by easy I mean that I can check fast, meaning polynomial time, polynomial in the size of the input. We have discussed that easy is kind of associated with polynomial time. These are things that I can do. So yes, you can show me every possible split of the graph. Yeah, and you can tell me, hey, look, in this split it's less than k. Hey, look, in that split it's less than k. How many splits are we looking at? In how many ways can you partition a graph into two vertices? 2 power n. Yeah, 2 power n is expensive. Okay, so it's not an easily verifiable solution in that sense. Okay, it's expensive. It's going to take a long time. Not every problem is an NP. You can come up with examples of problems that at least don't obviously fall into the class NP. So just want to emphasize that so that you don't get carried away thinking that we're just looking at the class of all problems. But we're looking at the class of most interesting problems, okay, to put it vaguely. All right, so inside NP there is a nice little class called P. These are problems for which we can not only verify a solution, we actually find a solution easily in polynomial time. These are problems that you're familiar with. You've met many of them before. Sorting, MST, shortest paths, interval scheduling, matrix multiplication, blah, blah, blah. The whole bunch of things that you do in a typical first algorithms course is this class P. Okay? But there's this big bad world outside the class P, which is what we're going to encounter now. Okay? These are problems that we're kind of clueless about. Okay? These are problems that haven't yet been classified in P, and for many of these problems we actually don't know if there is going to be a polynomial time algorithm ever. Some of these problems are known to be especially hard. Okay? They even earn the badge of being what's called NP complete. Heard this term before? What does it mean? Okay, every problem in NP reduces to an NP complete problem. That means you solve an NP complete problem, then you solve every problem in NP. That's kind of a big deal. Why do you think that an NP complete problem exists? Yeah? Any hawker can come along and define anything, right? I mean, it's such a strong definition. It's not at all intuitive that an NP complete problem should exist. If somebody comes along tomorrow and says, here is the definition of an NP complete problem, you're going to say, oh, okay, but where is such a problem? Do you know of an NP complete problem? What's an NP complete problem? 3CNF, okay, click, problem set 2 from that talk, yeah, everything in problem set 2 from that talk was an NP complete problem. But how do you know? How did he manage to convince you that every problem in NP actually can be solved? So suppose you solve click. How will you solve TSP? Have you seen the reduction? Okay. Okay. So maybe TSP can be polynomially reduced to click, and I show you a reduction. What about independent set? What about some other problem? Like thousands of problems in NP, right? To convince you that a problem is NP complete, I'd actually have to run through each of those thousands of problems and individually show you that they all reduce to this problem that you have. Feasible? No. Yeah? So that's why there is a theory, what we call complexity theory, which abstracts out the notion of what it means for a problem to be an NP. Okay, and that was the Turing machine model of computation. You say that any problem in NP can be encoded as a Turing machine acceptance question, and this problem reduces to satisfiability. So take any problem in NP, Phrase it as a Turing machine acceptance question. Reduce that problem to SAT, and then solve SAT, and then solve that problem. That's the sort of game you play. Okay? So this is what happens when you solve an NP-complete problem in polynomial time. Everything goes away, and you're only left with P. Okay? That's why people don't expect polynomial time problems, algorithms, for TSP. Because if you solve TSP, you're not only solving TSP, you're solving every freaking problem in NP in polynomial time. People don't expect that. Okay? So if TSP only carried the baggage of being an open problem that's been hard for several hundred years, and you solve it, people won't be that shocked. It'll make news, but this has happened before. Fermat's last theorem, Poincaré's conjecture, problems that have been open for several decades or centuries have been solved suddenly by a single person. So that won't be so shocking. But when you solve every single problem in NP, okay, people just don't expect that to happen. All of these NP-complete problems are carrying a huge baggage of difficulty with them. Okay, it's an extremely dangerous and potent definition. So that's why people don't try to come up with polynomial time algorithms for these problems. Okay, and I'll just give you a concrete example of a reduction, just so that we kind of know what's going on. So typical day at work looks like this. You have a problem X, okay, which you want to solve, either for an assignment or for those of you who are doing jobs. This is kind of the order from the boss. Come up with a polynomial time algorithm for X. You try for several weeks, and your career and reputation is on the line, and you're not able to come up with a polynomial time problem. What do you do to save your job? You say, hey, I'm going to come up with a polynomial time algorithm for TSP. Okay? Sounds like a tall claim, but what you're going to do is use a polynomial time algorithm for X as a black box. Okay? That's what a reduction means. Suppose somebody is able to solve X in polynomial time, then I will show you how to solve TSP. Okay? Show this to your boss and tell him, well, I don't have an algorithm for you today, but if you fire me today and hire somebody else tomorrow, he won't be able to give you an algorithm either. Okay? Because if he gives you an algorithm, then I will give you an algorithm for TSP, and we'll all be rich and famous, which is unlikely. Okay? So that's the argument. What does a concrete reduction look like? Let's try an example. Remember independent set? This is a collection of mutually non-adjacent vertices in a graph, right? Vertices that don't have any edges between them. Remember clique, it's exactly the opposite notion. Every pair of vertices have an edge between them. Okay? Both of these problems are supposed to be hard. I'm just telling you that. But suppose now you're in a situation, for the sake of story, where you're asked to solve clique. Okay? And everybody knows that independent set is somehow tough. Okay? And suppose you want to convince somebody that, hey, I couldn't solve clique, but if you can solve clique, then I can solve independent set. How? Suppose I give you an algorithm for clique as a black box. You can use it as many times as you like, polynomially many. How will you devise an algorithm for independent set based on the algorithm for clique?
You reduce that to clique.
How?
First you take the input to the input that have converted to the input of the clique.
Yes, but how? What's the conversion? What's the concrete conversion that you do? Remember that the notion of an independent set is exactly complementary to the notion of a clique. Okay, so you have a graph, and somebody has given you an algorithm for clique, and you are desperate to find an independent set. How will you use the algorithm for clique to find the independent set? Yes. Yeah. Good stuff. Take the complement of the graph. The clique becomes an independent set. The independent set becomes a clique. Correct? Everyone with me? When you complement a graph, every independent set becomes a clique. Every clique becomes an independent set. Now feed this to the clique algorithm. It will find you a clique. Wherever there is a clique, there is an independent set in the original graph, which you can return. Okay? That's the sort of stuff. Yeah? That's an algorithm. That's an algorithm that tells you that if you give me an algorithm for clique, then I'll give you an algorithm for independent set. Therefore, I don't expect you to give me an algorithm for clique. And therefore, I don't feel too shabby about not solving clique. Should you be gloating over this achievement? What does it mean for an engineer that a problem is NP-complete? Here's a problem that he needs to solve. You go and say this to your engineer friend, the conversation is going to end right there. Yeah, they don't care about if you can do this, then you can do that, then you can do that, and the whole world will collapse. They have a problem that they need to solve, yeah? And it's our responsibility as algorithmists to give them these problems, okay? All these problems in NP, they're not random puzzles that we are just enjoying out here. They are problems that we borrow from the real world, and we owe it to the real world to give them solutions. That's our job as algorithm engineers, yeah? Thousands of problems in NP. Many of them are motivated by problems that people need to solve. Theoretically showing a problem is NP-complete is not the end, it's just the beginning, yeah? It's a theoretical insight, it's an important one, there's no doubt about that. It at least tells you that there are things that you cannot hope to do. But now the question is, what next? Here's how people have been managing so far, yeah? What's a heuristic? Some algorithm which is what? Based on previous experience, yeah? Right. So heuristic, it's pretty much it. A heuristic is just the first thing that occurs to you when you see a problem. Several of you have come up with heuristics in this very room over the last 4 days. When you were asked for a job scheduling problem, somebody was like, pick the job that takes the smallest amount of time. Very natural thing to do. Yeah, so that don't waste too much time. Yeah, pick that job, choose it. Get rid of everything that conflicts with it. Then choose the next job that takes the smallest amount of time. When you were asked to find the chromatic number of a graph or partition into independent sets, then you said, okay, let's pick the largest independent set, throw it away, let's pick the next largest. So all of this stuff falls under the broad category of heuristics. Yeah? They don't necessarily work. As you have already been told, there are instances on which these strategies are going to fail. Of course, right? Heuristics are typically polynomial time algorithms. Because they're really simple, they're easy to implement, and they're usually polynomial time. At least in the context of NP hard problems, you don't expect them to be correct most of the time. Or you don't expect them to be correct all of the time. But they just kind of sort of work. So imagine that job scheduling was a hard problem. It's not, but imagine that it was a hard problem. But imagine that by applying this heuristic of picking the smallest job, gives you 5 jobs, and that's all that you want to do in a day. You're happy if you have 5 jobs. Is it going to really bother you that the optimum was actually 6? Don't care. You just need to have something that you can go by, right? Especially as Indians, we know that something that works for now is good enough. Good enough is good enough. Okay, that's kind of the driving philosophy of a heuristic. Optimum, okay, who cares? Yeah, let's just go with whatever we can do. So what's the problem? Why am I only halfway through my talk? And why aren't we just packing our bags and living with easy, simple, intuitive algorithms? Okay, those of you who are mathematically inclined are already probably feeling a bit scandalized. Yeah, and you kind of want your money back because what am I saying here? I'm saying do arbit stuff and try to get away with it. Yeah, doesn't make a lot of sense if you have this formal style of thinking. Okay, a more serious, so let me just pin down that vague feeling. There's this vague feeling that something doesn't feel right about heuristics. The specific problem is that it's, generally speaking, very difficult to formally analyze heuristics. Okay, why do we need a formal analysis? Why bother? Why have sorting algorithms been analyzed to death? What's the use? Prove their efficiency and also compare, right? You have any number of ways to solve a given problem, okay? I have to schedule my jobs for the day. Potential clients are waiting for a confirmation call, okay? And me being me, I haven't done anything yet and now I'm in a real rush to figure out my schedule. I come and ask you for help. You say do something, you say do something else. And I only have time to implement and try out one algorithm because folks are waiting, yeah? How do I know? How do I know which one to choose? It's anybody's guess, right? If you're giving me heuristics, it's just anybody's guess. Okay, and I just had to rely on my luck where I've stumbled on the better strategy. On the other hand, you tell me that my algorithm takes order n square time, you tell me this one takes order n time, I know which one, I at least know which one's going to run faster. At least as a ballpark estimate. Okay, so formal analysis, damn useful, and when you try it on heuristics, most of the time, you're left with very little to go by. You hit a blank. Yeah? So that's why a lot of algorithmic effort in recent times is devoted to figuring out how you can formally analyze all of these ideas that are floating around, these simple natural ideas. Yeah? Everyone motivated to go beyond heuristics? Yeah? Okay. All right. So here's how you begin semi-formally. You know that you have polynomial time. Okay, this is kind of an unbeatable truth. You can't afford anymore. This is all you got. Now you work backwards from here and try and see what is the best that you can do in polynomial time, provably. Yeah. So the first piece in the toolkit is approximation and randomization. Okay, you've sort of seen glimpses of at least randomized algorithms yesterday. And an approximation was mentioned. So in approximation, the idea is to say that, okay, we're going to relax our obsession with opt. Okay, we're going to follow along with opt as much as we can. And we may not get to opt, but we won't be very far off. And I'll prove that we won't be very far off. Okay, we'll see an example of this in just a few minutes. The next kind of situation that you might be in is that you can't afford to let go of opt. Okay, when we were talking about motivating program analysis and verification, you saw that software and algorithms often drive critical missions. People's lives depend on it. You can't just say, hey, let's manage. It's going to cause a heart failure, then you can't just manage, right? You need exact solutions in some situations, in some special critical situations, and probably as a result, in practice, you also have more resources devoted to the problem if it's a critical problem, right? So chances are that you can do a little bit more. One of the things to do in such a scenario is to see if your input has some special structure. All these NP hardness kind of fundebazi is for very, very general situations. Okay? It's hard to find an independent set given an arbitrary graph. Do you always have a completely arbitrary graph? You don't. Usually your graph might have some structure that you can peek into, exploit, take advantage of, and come up with a faster algorithm. What's one example of exploiting input structure that you've already seen? Something was easy on interval graphs. Nobody? The scheduling stuff we've been talking about, classroom scheduling, what was the problem? Coloring. Chromatic number. Finding the chromatic number is known to be a notoriously hard problem on general graphs. But if you're just going to use it for classroom scheduling, the underlying graph turns out to have a very simple structure. It would be foolish to not exploit it and say, oh no, this problem, it's an NP-complete problem. Okay, so exploiting input structure is the next thing that you can do. So this formally often goes by the name of parameterized and exact analysis. It's just some buzzwords for you to take away to tell your friends back home. Yeah, but okay. Chromatic number is easy not only on interval graphs, it's relatively easy on planar graphs. Why? Four color theorem, yes. You know that any planar graph can be colored with 4 colors. Interestingly, given a planar graph, to figure out can you color it with 4 or can you color it with 3 is an NP-complete problem. But in most real-life situations, do you care? You usually have 4 colors to go by. Okay? It's also easy on bipartite graphs. Remember bipartite? Why is it easy on bipartite graphs? 2 colors. It's easy by definition. A bipartite graph is a graph that can be split into 2 independent sets. It's easy by definition. Don't take bipartite graphs for granted. Somebody was talking about dominating set yesterday. Dominating set is NP hard on bipartite graphs, NP complete on bipartite graphs. There are problems that are extremely hard on bipartite graphs, but in the case of chromatic number, it just turns out that stuff is easy. Okay, a good solution often involves several approaches, so don't box yourself into being a semi-definite programming-based approximation algorithmist. You need to know a little bit about all kinds of strategies to be able to solve a problem on any given day in any given situation. Okay, it's always good to know what all kinds of algorithms involve, because at the end of the day, if you're especially in a practical situation, it's going to be a combination of experience, heuristics, specific algorithms that you're aware of from before. Yeah. Okay, so for the rest of this talk, we'll grab one problem and we'll try and look at specific realizations of all these vague ideas that we've been talking about. And this problem is vertex cover. Anyone remember vertex cover, or have you seen vertex cover? Yeah?
The minimum set that covers all the edges of the graph.
Right. The minimum set that covers all the edges of the graph. What happens if you delete a vertex cover from the graph? If you delete all the vertices from a vertex cover, what are you left with? A vertex cover is a set that covers all the edges. That means that every edge in the graph has at least one of its endpoints in the vertex cover. So, complement of a clique, independent set, right? You delete a vertex cover, you're left with a graph that has no edges. Why? Because if there was an edge, then you didn't start with a vertex cover. Every edge is supposed to have one of its endpoints sitting in the vertex cover. So you delete a vertex cover, you're left with an independent set. Okay, here's some toy motivations for vertex cover. There are serious applications, we'll just go with the toy one. Imagine that this graph is representing a road network where the edges are roads, the dots are intersections. Okay, and imagine that you are given the task of placing gas stations or petrol bunks at the intersections in such a way that if you have a car on any road and it runs out of fuel, he should be able to drive to at least one of the intersections at the endpoints of the road to refuel. Okay. Now, obviously, you don't want to place too many petrol bunks. Yeah, it's expensive to set them up. You can obviously place a petrol bunk everywhere. Problem solved. You don't have that kind of money. You're on a budget, so you want to find the smallest set of intersections where you place your petrol bunks. What's this problem? Right. No points for guessing. Yeah, this is vertex cover. Every edge needs to be hit at least one of the endpoints. Okay, the problem is the minimum vertex cover problem. Again, no need to be especially obsessed with the minimum. You have a budget. See if you can meet the budget. If the optimum is much less, nobody is going to know. Yeah, that's usually the way we talk about these problems. Is there a vertex cover of size at most k? That's all that you care about. We'll come back to that in a minute. But for now, all right, slightly redundant. This is the definition. Let's come back to the problem. Let's focus on a single edge. Okay. What can you say about any optimum solution? Okay, we are trying to approximate an optimum solution here, let's say. What can you say about any optimum solution with respect to this edge? Can any optimum solution afford to leave out both the endpoints of this edge? No, because then it's not a solution. Forget optimum. Yeah? Any optimal solution must pick at least one of the endpoints of this edge that's in focus. Okay? Now you don't know which one. That's the problem. So what do? Okay, after the talk on randomized algorithms yesterday, what would you do? Toss a coin. Two choices. Heads U, tails V, if the edge is UV. Yeah? It's a very natural strategy. But here, suppose you think you're approximating opt, right? You know that opt is going to pick at least one, you pick both. Okay? So you're going to be off from the optimum by sort of a factor of 2. Let's see why. Every time, so you pick both the endpoints in your vertex cover, okay, and get rid of all the edges that are incident on these endpoints because you have them all covered, right? I don't know if you saw the isolated vertex falling off, but if a vertex becomes isolated, meaning no edges incident on it, then you can freely delete it from the graph, right? Because it's not going to serve any purpose. A vertex with no edges incident on it cannot cover any edges, so you don't care. Throw it away. Yeah. Go to the next available edge. Again, pick both. At every stage of this algorithm, you're going neck to neck with the optimum. Yeah. Every time you know that opt is going to pick one, you pick two. Okay. At the end, you have a solution that is at most how many times the optimum? At most twice the optimum. Clear? Clear to everybody? Okay, so this is sort of a run of the algorithm. Okay, Okay, at this stage I've kind of picked vertices in the vertex cover. Now you run these algorithms and practice with your eyes open. Okay, you just don't, so at this stage, yeah, okay, yeah, we'll do that in just a moment. So once you've arrived at this scenario, I only noticed this while making the slide. After getting rid of all these vertices, dumping all of these guys in my vertex cover, the graph that I'm left with happens to be a very simple graph. Okay, it's just a bunch of paths. Okay, paths are just sequences of edges. Yeah, there's nothing else going on here. Now, think of it as a fun exercise to verify that on a path, the optimum vertex cover is actually just alternating edges. Actually, another way of thinking about it is that a path is a bipartite graph. Okay, all the alternate vertices go into one partition, the rest go into the other partition. If you think about it a little, okay, so it's actually a bipartite. It's actually a bipartite graph. And why did I mention that it's a bipartite graph? We only know that chromatic number is easy on bipartite graph. Turns out that vertex cover is also easy. Okay, and so there's the good reason to believe that you can actually find the optimum vertex cover by just picking the alternating vertices. I mean, it's intuitively appealing, and actually prove it formally. Okay, so at this stage, I just got bored of drawing more orange lines, so I just picked out the alternating vertices. Okay, if I'm doing something optimally, I don't have to bother about a guarantee, right? I'm just doing as good as optimum. It's even better. Okay, the factor of 2 thing. Look at the orange edges. Do they look like anything that you have heard about before in the P versus NP talk? Problem set 1, there was a problem called maximum matching. Remember? What was the matching? Disjoint edges. Edges that don't share vertices. Okay? Collection of edges that are completely disjoint. What do the orange edges look like? Do they look like a matching? Yeah? They don't share edges by definition, because once you picked one orange edge, you got rid of all the other edges incident on them. So when you pick the next edge, it's automatically disjoint. Yeah? Okay. Now when you have a matching, okay, so let's say that you're staring at a matching in a graph. What can you say about the size of the vertex cover relative to the size of the matching? You know that a vertex cover has to hit every edge. Yeah? Can a single vertex hit 2 edges from a matching? No. By definition, right? These edges are disjoint. They don't have a common vertex. So no vertex can hit 2 edges from a matching, meaning that every edge in a matching demands its own vertex in the vertex cover. So the size of the vertex cover is what? Twice? At most twice. Yes, because you can just pick both endpoints of the matching. We'll come back to that. But more importantly, I'm interested in lower bound because I want to compare with opt. So any vertex cover, and in particular the optimum vertex cover, has size at least the size of a maximum matching. There is no getting around a matching. Okay, if you have a matching on k edges, any vertex cover has to have size at least k. Is that clear? Because every edge in the matching, okay, must be represented separately in the vertex cover, must be hit separately in the vertex cover, right? So any vertex cover is going to have size at least k. Okay, so you're staring at a matching here. What is the size of your solution? What's the size of your solution? 2 times the size of the matching, right? Because you've taken every matching edge and you've picked both endpoints, right? So opt is at least k, your solution is at most 2 times k. That's the factor of 2. Okay? Any solution at this stage, so the other way of looking at it is during the run of the algorithm, you realize that from every edge, any optimal solution, no matter how mysterious, is picking at least one of the endpoints. All you're doing is picking both, right? So opt had at least 1, I have at most 2, right? So you're kind of over approximating the optimum just by a factor of 2. Okay? And if you think about it, you'll see that the edges that you encounter during the course of your algorithm actually form a matching. Okay? So a formal way of saying this is that, well, any optimal solution must be at least the size of the matching, my solution is at most 2 times the size of the matching. In fact, it's exactly twice the size of the matching. So I'm off from opt by a factor of 2. Is everyone with me? Yeah?
Approximate to any extent you want.
Right. So we talked about TSP, and there was an epsilon somewhere out there. We said that TSP can be approximated to a factor of 1 plus epsilon in a certain kind of running time. You remember this? One of the slides in the past, couple of days ago. There was an algorithm by, I think, Sanjeev Arora, n to the 1 by epsilon. That's the kind of time you need to spend, and you get a solution that's off from the optimum by only a factor of 1 plus epsilon. Now the epsilon is a parameter that's in your hands. Okay? The smaller the epsilon, the better the approximation and the worse the running time. That's a natural trade-off, right? You want a better approximation, you pay for it in the running time. You spend more time in approximating better. Yeah? So some problems have these infinitely approximable algorithms, right? You can just keep approximating for as long as you wish. Vertex cover doesn't fall into that category. 2 is the best factor approximation that we know of. This stupid simple algorithm is the best that we can do. It's NP complete to approximate vertex cover better than a factor of 2. That's a slightly complicated statement to make, but people just don't expect that there'll be any algorithm which approximates vertex cover better than a factor of 2. Okay, I don't know if it's quite NP complete, but if you can approximate vertex cover better than a factor of 2, something super unexpected happens, something like P equals NP.
You can actually try depth first search and choose the alternate vertex.
Sure. But again, like we have said, that's more along the lines of a heuristic. You need to prove. So if you claim that that's going to give me a 1.5 factor approximation, you need to come up with a proof. That's not obvious. Yeah? You first of all need to prove that every edge is shearly covered, and then you need to prove this relationship with opt. Okay? What is any optimum solution doing?
Doing a depth first search, all this is obvious, balancing all the.
If you pick the alternate vertices in a depth first search, sure. Sure, but I think you can, it's not very hard to see examples where you'll do badly. Because it depends on how you're picking. So if you have a star, right, what's a star? It's one vertex with many edges coming out of it. Okay? This is vertex cover of size 1. But depending on how you do your depth first search, you might end up picking more. Yeah? So think about it. Okay. Mm-hmm. Yeah, it's kind of reductions, but these reductions are a little more intricate. They're not quite as straightforward as the ones we saw. Again, there is a starting point. Like we said, that some problem is NP complete, like satisfiability is NP complete. That was a non-trivial proof, by the way. Satisfiability was historically the first problem shown to be NP complete. That Turing machine kind of beast reduces to satisfiability. So that was historically the first problem. And then, of course, the whole industry opened. People reduce SAT to all kinds of things. So similarly, there are canonical problems that are hard to approximate. That you show from first principles based on various assumptions. So the whole NP completeness business is dangling on the assumption that P is not equal to NP. That's a nice assumption that all of us believe. In the context of approximation, the assumptions can be different. Sometimes it's just that P is not equal to NP, but there are other assumptions. Something called the unique games conjecture for people who want to look it up. There are various other assumptions that go into the basis of the belief that you can approximate vertex cover better than a factor of 2. Yeah, but essential tool is still reductions. Questions? Okay.
So when you're claiming that this can't give a better algorithm, so you have tried all the algorithms and you're showing that this is better than another.
No, that would again be kind of tough to do, because the space of all possible algorithms is huge. So that's not quite what we are saying. But when you say that there is no polynomial time algorithm for TSP, remember this kind of dramatic justification that we made for it. If you solve TSP, then blah 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 blah. It's that sort of thing. If you approximate vertex cover better than a factor of 2, then probably you can solve TSP in polynomial time. It's that sort of argument. Yeah? Okay. Yeah? Should we move on? Okay. So So we've seen what an approximation-like strategy looks like. The other strategy we mentioned was to exploit input structure. Like I said, you've already seen one example, which is interval chromatic number. I mean, chromatic number and interval graphs. We'll see another kind of structure exploitation here. Here, the structure that we're assuming is not very strong. It's actually a very natural assumption. The assumption is that you're looking for a small vertex cover, that K is kind of small. Okay. Of course, this is a vague statement, but we're talking about algorithms that can be potentially implemented in practice. So in practice, somebody tells you that, okay, you can install like 7 gas stations. What's the best that you can do, right? So you have a fixed budget. You're working with respect to that budget, and that budget is usually small. That's intuitive to everybody. Most of us are tight on budget, right? So budget is kind of small. That's intuitive. Yeah. So let's say that K is small. Just keep this at the back of your mind. We'll try and come up with a strategy that exploits the fact that K is small. Okay, what's a natural heuristic for vertex cover? Like you were saying, depth first search is one thing that you can do, although I think of that as a kind of complicated algorithm. What's the most natural thing that you can do? You're trying to cover the edges. You're trying to hit every edge in a graph. What sort of a vertex would you be most pleased to include in a vertex cover right away? Highest degree, yeah. The degree of a vertex, number of edges that's incident to it, right? So the highest degree vertex is a very natural starting point. Everyone agree? Yeah. It's just like when you were doing max cut, you would put guys who have more friends on one side and try to push all their friends to the other. You're maximizing the size of the cut. Similarly, for vertex cover, you're trying to cover the edges. So pick the guy that covers most of the edges, right? There's no reason to not go with this intuition. But that would still fall under what we called heuristics, right? Here's a way of attempting to analyze this heuristic, okay? Let's see if we can make this a little bit formal and where we get there. So rather than just saying pick a high degree vertex, what can you say about a vertex that has more than K neighbors? K is the size of the vertex cover that you're trying to find, okay? If a vertex is not just some high degree vertex, but it's a vertex that actually has more than K neighbors, it's covering more than K edges. Can you say something like certainty? Mathematical certainty. Can an optimum vertex cover not pick this vertex? By optimum here I mean a vertex cover of size at most K. Can a vertex cover of size at most K afford to leave out this vertex? No. Why? This vertex is doing way too much work for you. You can't let go of it. If you let go of this vertex, you don't pick this vertex, then you're still left with the job of covering all of these edges. And now the only way to cover all of these edges is to pick all the other vertices at the other endpoints of these edges. Okay? Every edge has only 2 candidate vertices that can hit it. Okay? If you don't pick this guy, then you're forced to pick all the others. There are too many of them. There are more than K of them. You have a budget of K. Okay, so it's, I don't know if I'm actually.
If I can take an example, suppose top 4 are connected to one other vertex and the rest 2 are connected to some other vertex. This is connected to some other vertex. So you have 3 which is covering all the edges.
Right. Sure. Okay, I can actually draw out your example and go through it, but let me try to convince you a little more easily. No matter what else is going on in the graph, you leave out this vertex. Yeah, you leave out this vertex, you have to pick more than K vertices. Just imagine that K is a hard budget that's given to you by your mom. You cannot spend more than K. Yeah, you don't pick this vertex, you spend more than K. You have to take this vertex. Yeah, so this is no longer a heuristic. It's something that you can say for sure. Any solution of size at most K must involve this vertex. So let me pick this vertex. It's the natural thing to do. Okay? Fine. Pick all vertices that are seeing more than K vertices. Okay? These are your high degree vertices now. Okay? Throw them away from the solution. Everything that they're covering, you're happy. Okay? So obviously when you pick these vertices, you decrease your budget, right? You don't get to pick these vertices for free. You pick a high degree vertex, K becomes K minus 1. Yeah? So the more high degree vertices you pick, the lesser the remaining budget. Okay, what if there are more than k high degree vertices? What if there are more than k high degree vertices? Look, we asked a question. Does this graph have a vertex cover of size k? You don't have to always go out and find a vertex cover of size k. Less than or equal to k is what I meant. Sorry. You don't always have to go out and find a vertex cover of size at most k. What's the other thing that you can do? What's the other possible response to this question? Increase your budget. Yeah, you're kind of getting there. Let's say that the budget is fixed. Does this graph have a vertex cover of size at most k?
You can show it contains less than k also.
Well, there are more than k high degree vertices, right? It definitely cannot be less than k, because you're actually, you know for sure that every high degree vertex has to belong to your solution. There are more than k of them. Your budget is k. What is your natural conclusion? There are two ways of answering a yes-no question. One is yes. What is the other answer?
No.
There is no vertex cover of size k in this graph. Yeah, because at every step you are sure that you must pick this vertex, you must pick that vertex. Now you must pick more than k vertices. You have a proof that the graph has no vertex cover of size at most k. You can say no. There are two ways of answering this question. Yeah? You go back to your boss and say, hey, you give me 7 gas stations, no way of placing them such that every road is covered. And I can show you why. And you can explain this to him over coffee. Is this a difficult argument? So you say no. If there are more than k high degree vertices, you say no. Otherwise, you have a remaining budget. Okay? So let's say that the high degree vertices are gone, and you have, let's say that there were x high degree vertices, so your remaining budget is k minus x. In the remaining graph, what's the property of every vertex? No vertex is high degree. Every vertex is covering at most k edges. Okay? This is kind of a handicapped graph. Every vertex now has a limited power on how much it can cover. Okay? So now suppose in this graph, you have more than k times k minus x edges. Okay, suppose after picking all the high degree vertices and having some budget left, you're looking at this graph, and the graph is huge. It has lots of edges, and you have a small budget. What can you say? Intuitively, if every vertex cannot cover a lot of edges and you have a lot of edges to cover, sure, you try to cover as many as you can, but again, formally, you're just asking the question, does the graph have a vertex cover of size at most k? No, no, it doesn't, right? Because any vertex can take care of only k edges. Your remaining budget is k minus x. Pull everything together. Take any set of k minus x vertices. Together, they can cover at most k times k minus x edges. If you have more than these many edges, you again have a proof that there is no vertex cover of size k. Right? So right now, locally, we're just interested in answering a very specific question. You have a graph, you have a budget, can you do it? You answer this by saying yes or no. Okay? Of course, when you say no, there are natural next steps. See if you can increase the budget. Quarrel with your mom. Say no, there is no way I can do this with k. Give me k plus 1. You can do all of that, but it's the next step. After you know for sure that you cannot do it with k. But first you need to prove that you cannot do it with k. Okay, so if your graph is huge, it has lots of edges, more than k times k minus x edges, then you can say no. Otherwise, the graph has at most k times k minus x edges. Yeah? And remember our starting intuition that k is small. So now you only have something like k square edges. And k is small, it's like some small constant. Take your favorite brute force algorithm and run it on this graph. It's a small graph. This is where you're exploiting additional information in your particular situation. Okay? Theoretically speaking, k can be as large as n. There are graphs where the smallest vertex cover has size at minus 1. Example? graph on n vertices which needs n minus 1 vertices to cover all its edges. Complete graph, right? If you have all the edges that can be there, naturally need a large vertex cover. So technically speaking, k can be as bad as n. So if I just had to write down k times k minus x is at most what? It's at most n square. Number of edges is at most n square. Big deal. Everybody knows that. But the additional insight is that you start off with the idea that you have a small budget. And that's what makes this slightly, it's somewhere in between a formal analysis blended into the setting of a practical situation. Okay, so work with the intuition that k is small and you're kind of in business. Did this make sense to everyone? Yeah? Some of you have probably heard terms like pre-processing, data reduction. It's that sort of thing. You're trying to do whatever you can to intuitively to make your data smaller. Okay? Now you can actually formally prove that after doing all these natural things that occur to you, your data actually becomes small. Or you have a good reason to say no, that you cannot do it at all. Right? So at the end of the day, you have a small instance or you have a good reason to reject the instance. Okay? In either case, in either situation, you're happy. Are you happy? Seeing the sea of glum faces out here. Okay. Okay, I hope that kind of sort of made sense. Yeah? So let's just recap the toolkit that we have for dealing with hard problems. First, the first thing is your common sense, heuristics, the first thing that occurs to you. With some experience, you try and see if you can get inspired from your heuristics and analyze them. You can analyze them by seeing if you can approximate the optimum, or if you can randomize whatever it is that you have to do, or if you can exploit additional structure in the input. Okay? And now you can talk to your friends who are engineers. All right? Thank you for listening. Questions?
Any questions?
The algorithm I followed, you are
And
bound
just a
to
minute.
get, with the algorithm you followed, you're bound to get twice the optimum solution for the vertex car. Is there a possibility like you can take the half of that vertex car and try all the subsets of the thing and
Sure.
do that in a polynomial time?
Sure. Yeah, so you have actually, this is in fact a strategy that's actually used. So the approximate solution gives you a vertex cover of size 2k, right? You can see if you can use this solution as a guiding light to find the optimum. Okay? You have 2k vertices with some special property. They're already covering all the edges. See if you can try all subsets. Now your optimum vertex cover may not actually be a subset of this guy. There is no guarantee on that. It may not precisely be a subset, because it may choose to pick something else. You pick the edges in some random sequence, right? I mean, not random, in a completely arbitrary sequence. I started with some arbitrary edge, okay, and then I picked both of them and everything incident on them went away. Maybe one of the things that whenever you saw the isolated vertex falling down, maybe that was an opt, okay, but I got rid of it, okay. So the opt doesn't have to be a subset of these 2k vertices, but at the same time you can...
Subset of the k vertices, subset of the entire graph.
Correct.
How to know it's k vertices?
Right. Right, so you know that there is a solution of size k, you have a solution of size 2k. You can try to splice these two things together, okay, and see if you can actually improve your solution of size 2k to a solution of size k. Now, even intuitively, just what you said, try all possible subsets of 2k, that's already 2 power 2k or 4 power k. That's kind of exponential time in k. Again, if you just write down worst case, k is at most n, that becomes something like 4 power n. However, if you continue to use the intuition that k is small, okay, notice that 2 power k is polynomial if k is like log n, right? So if k is kind of smallish, these strategies are actually feasible and they're actually used. Much of the stuff is actually implemented. I mean, vertex cover has serious motivation from bioinformatics applications, yeah, and a lot of those people write a lot of code, and many of these things are actually implemented, yeah. Anything else?
Any other question?
So when you approximate the LP hard problems, there won't be NP anymore.
No, they continue to be an NP because an approximate solution is not a solution, right? It's not an optimal solution. You still haven't found. So for example, if you just take, Just take a graph which is a matching, right? Just a collection of some n by 2 disjoint edges. Run this approximation algorithm. It's going to present you with the entire graph. What sort of an approximation, what sort of a solution is this? It's a crappy solution. Yeah. Okay, so basically an approximation algorithm solution can be extremely far away from the optimum. Okay, there are cases where it's going to be as bad as 2 times the optimum or whatever. So these problems continue to be in NP, but there is a further classification of problems in NP depending on how well they can be approximated. So people believe that TSP is in a separate category from vertex cover, because in vertex cover you cannot beat the barrier of 2. Somehow you're stuck at 2, whereas for TSP you can get arbitrarily close to the optimal solution. So of course these problems have different complexities. And that's what complexity theory is about. It's the business of classification. Okay, so you just try and get finer and finer classifications of that big bucket called NP. Okay, based on the kind of algorithms that you're able to prove, the kind of hardness results that you're able to prove. I hope that answers your question a little bit.
Does this also fall under the heuristics?
Does what fall under the heuristics? The last.
Yeah, the last.
So a lot of these strategies, these kind of strategies are inspired from heuristics, but because you're adding a layer of formal analysis, we don't quite call them heuristics. Okay, but the official, the official jargon, the name of the area is data preprocessing. It's kernelization if you want the term. So they're not exactly called heuristics. They're not heuristics because heuristics are typically, I mean, of course, beyond a point, this is just language, right? But heuristics are typically considered things which don't have any formal guarantees, whereas this stuff comes with a formal guarantee on what it can achieve and what it cannot achieve. Yeah.
So any other questions? Okay, thanks a lot, Neeldhara. That was certainly an engaging talk.
All right, thank you very much.
And if you guys want to catch up with Neeldhara, is a PhD student in our department. He works with Professor Jayant Haritsa.